Introduction. Physics teaches us that energy can neither be created nor destroyed. We know that in the case of ionizing radiation, exposure to that radiation results in a transfer of energy to the human body, which produces ionization of atoms and molecules. When that energy is deposited into living tissue, it produces excitations in the form of vacancies in electron shells in the atoms and molecules of the tissue. There is a chance that radiation could pass through the cell without producing any damage, but radiation could kill the cell or damage the cell as well. There's also a chance that damage could be repaired by the body. Unfortunately, the interaction of X-ray photons with different parts of the molecular structure of the tissue is somewhat random, and we can only estimate the probability of these interactions occurring. But it is important for us to know because these interactions can lead to permanent changes in the tissue which may result in unrepairable biological injury. We know that at the diagnostic level of radiation for medical purposes, small modifications of DNA structures can have widespread consequences for the cell because the structure of a DNA molecule can potentially be altered. The DNA constitutes the cell's operational instructions. Since DNA is replicated during mitosis, any type of mutation may occur in the cell structure or function, which could be very minor or quite significant. Because these interactions occur somewhat randomly, we can estimate biological effects from exposure to follow a linear, non-threshold dose pattern. In other words, we must assume that any exposure to radiation has the potential to produce a biological response, and as the dose increases, the potential for a response increases. The severity of a radiobiological injury is also clearly dependent upon the specific location of the initial radiation interaction.